Hi, I'm Joshua Reich, and welcome to Masterpiece Theater. Oh, sorry about that. Yeah, hey everybody. Thanks for rejoining us. We're a little bit of a smaller group right now. Maybe more folks will show up. We do have pretty soon another guest speaker, Srinivas, who's going to be telling us about some of the query functionality in Pyretic, going into that in a bit more detail, and the path querying library he built on top of that. Really neat piece of work. But before then, what we're going to do is spend a little time going over some things in Pyretic that we didn't touch on yesterday, or that we did. So the first thing is I'm going to do is take a little bit of time to just go back over the compilation. I don't know if everyone caught it. So I'm going into the code base here. We're in the Pyretic GitHub repository inside the subdirectory Pyretic. And we're going to go into core, where all of the action is happening. Now, let's see. We're going to peek back into the runtime, and we kind of went through this whole thing yesterday. And on line 199 of the current code base, master branch, you'll see update switch classifiers, which in proactive mode, lines 209, does a compilation. So this is all that cross-producting that we were talking about yesterday. And line 215, which does the installation of the classifier. So yesterday we had taken a bit of time to go through this first section, looking primarily in classifier.py, where we had our rules, that's a match and a set of actions, a classifier, which is just an ordered list of rules, and various composition operators that operate on classifiers. So I take two classifiers, and I can parallelly compose them, assuming they're OpenFlow, and this code is all for OpenFlow 1.0. So as we discussed yesterday, you've got a doubly nested induction over here with add. So basically, you say for each rule in the first classifier's rules, for each rule in the second classifier's rules, you're going to cross rule 1 and rule 2. If that produces some output, then you're going to append it to the list. And the cross basically involves taking an intersection of the matches and a set union of the actions.
Josh, sorry.
Sure.
Are you sharing the screen or not? Because we aren't seeing anything.
Oh my goodness. I apologize. Thank you for reminding me. I should have shared.
Don't worry, never mind.
What foolish of me. I'm just going to share the whole desktop. That was lame. I apologize. Okay, now you can see what I'm actually doing. So I'll just go back over this in the screen for a sec. We're popping back into the runtime. We're going to update switch classifiers, line 199. I was talking about lines 209, the classifier, where we compile the policy. This is cross-producting. And line 215, where we do classifier installation, which is more than just pushing the classifiers to the switches. So we're going to back up and pop into classifier.py, which is where we do this cross-product, where the cross-producting logic lies. Particularly, it lies in the definition of the classifier class. This is an ordered set of rules, each rule being just a match and a set of pyretic actions, modifies, we can call them, count buckets, so forth. Line 144 shows us how we do parallel composition, the addition operator on two classifiers. And basically, 155, we create an empty classifier. 158, we go over an outer loop of all the rules in the first classifier, followed by the next line where we go over an inner loop of all the rules of the second classifier. For each pair of rules, we cross them.
What is cross?
Yeah, so we take their cross product, and this is the parallel cross product, which is defined up above on line 146. And the parallel cross product literally takes the matches of the two rules, intersects them, and takes the action sets of the two rules and unions them. And that's what a parallel cross product is.
How does the underscore cross? How do you know that refers to the parallel cross?
Because it's defined within, exactly. That's how I do it, yeah. Cool. No, that's a great question. And now we see if there's no intersection, then we just return nothing. So if we haven't returned nothing, then we're going to append. So we'll append these crosses one by one by one, and then at the end we're going to do this optimize, which, as you'll recall, but I'm going over it again very quickly in case anyone missed it, is at line 284, and basically this is just remove shadowed cover single, which is 289, and basically this, I'm not going to go through the lines in here, but what this says to do is to go through the classifier. It's an n squared time algorithm that looks at the first rule and says, well, nothing covers this, throws it into the set of uncovered rules, then looks at all of the other rules with reference to the first, and, well, the second, well, it continues looking at the rules, and any of the rules that are unshadowed, not covered by some other rule, are put in the final optimized classifier. Anything which is covered by some rule which is in the optimized classifier is not put into the optimized classifier. So we remove all the shadows, and this is one algorithm for doing it. And you know, if you're interested in pulling apart that exact logic, I'm happy to you know, deal with that offline or fix up the documentation nicely. But so at the end of this, to combine two classifiers, parallel composition, you're basically just going to do a loop. You're just going to literally do cross producting the way you would do it in, you know, a matrix multiplication, except instead of multiply, we use this underscore cross, which in parallel composition is defined to do match intersection and action set union. Now, sequential composition, a bit more complicated. Again, we're going to go over this quickly, and I'm going to skip the helper methods and just focus on the high-level logic, which is, again, we're going to loop over all of the rules in the first table, and assuming that the first rule isn't a drop, that's what this special case is for, we're going to loop over all of the rules in the second classifier. So the special case, if the first rule ends in a drop, clearly it's not going to match anything in the next table. So there's no point in looping all of those rules and doing that calculation. But if it does produce some output, then that output is going to go into the second classifier. And so we're going to need to look at each rule in that second classifier. And here we're going to do a sequential composition cross. So again, this is just matrix multiplication. This is, you know, matrix multiplication, but multiplication is replaced by the sequential underscore cross. And same as before, we're going to do their optimize. So where's the magic in here? Well, the definition of the cross product for sequential composition is a bit more complicated. And as we said yesterday, for each action in the first rule's action set, we're actually going to do another cross product. And then we're going to need to get all of these things, and we're going to need to parallel compose them together, line 253. And so I kind of explained hand-waving about this yesterday. And what I'm going to do right now is just quickly show you an additional slide that I added to the slide deck, which is available at the Dropbox URL that I gave you yesterday in the email list, and is also associated with that if you go in Google and you look at events or Hangouts and you see this Hangout, it's actually there in the comments now. So this slide, sequential composition, let's say this is our first, our R1 classifier, or rather our C1 classifier. So we've got desc-mac on one side, we've got forward 1, forward 2 on the other side. So if it's A, then we're going to forward out both ports. If it's B, we're going to forward out 3. If it's anything else, we'll forward out 2. This might be, we might call this identity actually in the syntax of classifiers, but it's effectively the same thing. And note these forwards are pyretic forwards, so they just mean modifying the outport virtual field. So what are we going to sequentially compose this with? Well, another thing which is actually going to do stuff based on the outports. So if it's going out outport 2 ultimately, oh, we're also going to send it to a count bucket. And if it's going out outport 3, we're just going to send it on through. Likewise with the star, or maybe the star one, you know, can be dropped. I'm just making it different right now. So why is this whole action thing going on? Well, let's think about it. So I have a packet that matches desmac A, gets forwarded out port 2. So that produces one packet, which is the original, but now it's got out port 2, and a second packet, which matches the original and has out port 3. So we got these two packets. The first packet's going to get hit by this rule, the rule matching out port 2, whereas the second packet, the one that's going out port 3, is going to get hit by the middle rule, the one matching out port 3 that does identity. So when we do cross product, first we're going to cross desmac equals A forward 2 with all of these rules, and we'll get what we get out of it. Namely, the thing I was highlighting over here is it's definitely going to cross with this rule, and you're going to end up getting this guy out. It also will happen to cross with the star rule, which I've elided from the drawing. But so you'll end up getting two rules in this box. So you'll get a mini classifier. Likewise, with desmac A highlighting forward 3, so now we're doing the second action with that match. Well, this thing is going to drop on here because there's no intersection. It's going to have packets that could match this rule and also could match that rule. So again, we'll produce a mini classifier. Since this thing's drop, and since there are no packets produced by forwarding 3 that aren't going to match an out port 3, we're eliding the other rules in here. But we get classifiers who, when they're optimized, are this and this. So two separate classifiers. Yeah?
Oh, I see. The parallel comes from the comma.
Yeah, the parallel comes from the comma here. That's exactly right. So actually, if I want to fill this out, just to make sure I'm not being totally confusing, we'd have a second rule, desmac equals A, and this guy that is going to basically, drop, right? But or whatever it's going to do, drop and maybe some other stuff. But this is a shadowed rule because we're always going to hit this rule first. So I optimized and took it out. So these are the two classifiers that get popped out from just doing the cross of this rule with this table. And then what we need to do is, well, run these in parallel. So now we're going to do parallel composition on these two mini classifiers, outputting a new classifier that, well, does desmac A, right, intersect the two rules matches, and they happen to intersect to be the same thing, and union their actions. Does that make sense?
So whenever you have a same left-hand side, you always convert it into a comma-based single loop. So for example,
yeah.
You have desmac A and desmac A. Like, this means like these actions should be done in parallel, so you add a comma in there.
Yeah. So the way we're encoding, this sort of syntax, which I haven't fully defined, basically represents parallel composition using a comma,
So for example,
except not entirely. Here, if I write this out very carefully in real pyretic syntax, or in the subset of pyretic syntax that should be defined for classifiers, but I haven't because I was too lazy to do it. That's what it should be. Now, it turns out when you compile this down to OpenFlow, in OpenFlow, it looks like OpenFlow forward 3, comma, OpenFlow forward 2, comma, forward controller. No, it means kind of do this, do that, then do the next thing, but do this. The semantics of OpenFlow aren't as neat and nice. But so if I say modify, like if I were to put a modify here, that was a modify in an actual concrete packet header, like mod f equals v. So then after this, everything that gets forwarded would be the modified version of the packet in OpenFlow 0.1. So this means something different than does the same list, but it's f equals v over here. Because the packet that gets forwarded.
Is actually like the part of OpenFlow, like the way
yeah, this is kind of how, this is part of OpenFlow 1.0. When you get into latter versions of OpenFlow, there are actually a variety of different ways that you can have multiple actions applied. depending on whether you have them applied in the group table or in the actual action sets, and they offer a variety of lots of different mechanisms that do different things. So you might make a modification, and that modification takes effect on subsequent packets that are sent out, or you might make a modification and not have the modification take effect. And like it gets complicated if you read the OpenFlow 1.3 or OpenFlow 1.4 specs. But we're gonna leave that aside right now. I just wanted to give you to build a little bit more intuition. At some point I'm gonna make a full-on animation maybe, or someone else will. But this should give you a little bit more of a flavor into why sequential composition works the way it does and how it's a bit more complicated and in fact relies on parallel composition. So this is classifier, and what I'd like to do now quickly, that we've kind of recovered the material from yesterday, but in a very condensed fashion, and I hope I haven't left anyone behind, but if I have, feel free to ask me a question now. Okay, I'm going to assume I haven't left anyone badly behind then. We're going to go back into the runtime so you can see the second part of compilation. And actually, we'll just look for install classifier. There we go. Proactive compilation. Right now, line 321. We're probably going to get rid of the segment of code that deals with reactive compilation in here. Standalone reactive compilation. There are a variety of different types of reactive compilation. But let's not get into that right now. For right now, you have your classifier. It's been completely compiled via that optimized cross-product, recursive optimized cross-product process. And now, well, we need to do a bunch of things to it because it's still in this semi-abstract form. We need to get it down to a set of concrete OpenFlow tables which are actually sent out to the switches. And we also may need to do various things to it to make it appropriate to the particular topology of the network or to a variety of other issues. And in fact, we'll go through those right now. So install classifier defines a whole bunch of different methods. So one's removing identity. There is no identity in OpenFlow. So we're going to strip all of those out once we've done all of the compilation process. Because now, if you ultimately just have an identity sitting there, the packet will get dropped. So,
what do you replace it with? If you have an identity, what do you replace it with?
You replace it with a nothing.
That's a drop in actually.
It is.
Okay.
Yeah.
But identity means like you don't do anything with the packet and just send it out.
Well, identity means you don't do anything with the packet and you leave it as it is for the next thing to do something to it, right? But if ultimately nothing ever does anything to the packet, then it never gets an output assigned. Hence, it remains on the data plane switch forever.
Which in OpenFlow terminal actually.
Yeah. We don't actually just keep it there because no one can touch it, no one can use it, it's gone into a black hole. So in OpenFlow, that turns into a drop. So we have a remove identity that takes a classifier and returns a new classifier, each of whose rules now has its identity stripped. Likewise, we take any action, so controller of like, take controller of I can't pronounce that, replaces each rule whose actions include a send to controller action with one whose sole action sends packets to the controller. Now, this is an anti-optimization. So this is not the fastest way to do things. But the reason why this is done in the current version is because it's the simplest way to do them correctly. So let's say I have a packet that gets modified and then sent to a bucket and then forwarded out, right? So I could break this up into two pieces of logic, a piece of logic that modifies the packet and sends it out and then sends it to the controller. Or I could do it by sending the original packet to the controller and then modifying it and then sending it out. That's probably the way I'd do it because when the packet goes into the interpreter, like we saw before yesterday, well, it needs to know how to evaluate the policy. And if it's actually in the middle of evaluation of the policy, part of the policy has been applied by the data plane, the part hasn't, okay, how do you partially evaluate it correctly? That is tricky to get right, very easy to get wrong. And so we just take a side pass of that whole thing right now. Now, the optimization I showed on the slide yesterday, which I think is a very reasonable one, is by default, if you're going to send anything to the controller, you send just the original packet. You send the packet first to the controller without any changes or modifications to it, and just with that bucket tag that I had mentioned yesterday. So that would be the first optimization to implement in here. If it needs to go to the controller, send it out, then do all of the data plane stuff subsequent to that. But we're not there yet, so controllerify right now, its logic is even simpler, and what it does is it just removes all the other actions and has all the processing, both control plane and data plane, done at the controller. Make sense?
And then the controller would
inject the packets back into the network. Yep. So then there's a VLAN specialize. So, you know, OpenFlow's default, if we want to be able to do matching of packets on VLAN, it turns out if some of your packets aren't tagged with any VLAN, then you run into problems, even though, in my opinion, that's not how things should work, but who cares what my opinion is. This is the reality, so what we do is we make sure that we create a default VLAN match for each of the rules and kind of add it to all of the rules and, you know, make sure that every packet, all the rules get adjusted so we get around this particular problem and traffic flows exactly the way we say it's supposed to flow as opposed to not doing so. There's also a layer 3 specialization. Oh, question about that?
set a bug in OpenFlow.
I don't know. A feature, bug, it's hard to say. I wrote this code a really long time ago, so I'm not sure. I mean, there are a lot of, the OpenFlow routers which are available right now, the way they handle VLANs are just like horrific. Like you can modify VLAN headers and you can pop them, but you can't push them on. So they have to be put on by something else. And if you do it, they let you put a push in there. So the rule is supposed to be pushing the VLAN, but it just doesn't.
Right.
And
More than happy to do that right now, if you tell them to.
yeah, I mean, you know, yeah, they know how to do it, but the implementation, is it wrong? Is it, the OpenFlow spec sometimes is not, you know, I mean, it's not a formal specification either. So, but this is some of the stuff that, you know, when you're writing a controller and processing, when actually compiling, you need to do this stuff because of the way things work. So VLAN specialization, there's a layer 3 specialization. So like, let's say you do a match on a layer 2 field, like MAC address. Well, you expect it to match on, you know, that MAC address. Oh, sorry about that. To match on layer 3 rule to several rules that match on layer 2 fields. Oh, sorry. Let's say I do a match on IP address. Well, it turns out that there are a bunch of different packet types that can match on IP address. And you have to specify the packet type in order to do the IP match, even though they're multiple. So what we do is, for each rule that we find that matches on IP, and perhaps doesn't match on Ethernet or doesn't specify the type already. So there's some logic in here, and I'm not 100% sure it's right and all correct in all corner cases, but it's pretty good. What we're going to do is we're going to create additional rules that will you know, match on a couple of different a couple of different types. So ARP types or IP type, Ether type, IP type, Ether type, ARP type, etc. So this is the logic in layer 3 specialized. Then there's bookkeeping, the buckets. So this is if you're,
So it's like,
yeah.
that part seems like you are building a state machine of yourself. Like because in packet processing, you have to go through these different layers to make sure that if you want to extract IP address, you have to have an Ethernet type of an IP address. So in this case, you are doing sort of again, going through some sort of state machine. Though you are not doing parsing because it's already there. But
you could think of it that way. I mean, I think there are a variety of ways to think about it. You know, for me, it's just like, this is what we had to hack out to get it working. But I think, you know, something more principled than that would be very nice.
Well, why do you have to do that? Like, why do you have to translate the layer?
Oh, so basically, so just high level, if I say match, if I match source address 10.0.0.1, So, and I put a rule in the flow table that matches on that. The flow table will let me put that rule in, but no packets will match it.
Why?
None. Yeah, because the ether type's not set correctly. You need a.
I think it depends on the data plane architecture as well.
It depends on the data plane architecture.
Software with what they are doing, I think, is they are actually going through the packet again. So they have to make sure that if you want to jump to layer 3, you have to have IP types in the layer 2. But if you have a fixed packet vector in RMT case, you have a fixed structure.
Yeah.
So if there is some non-zero value in the IP3 section or bits, then you have.
Yeah.
Yeah, that
So,
seems like a,
well,
like a OBS bug or something.
well,
It seems like,
you know, you can
why
call.
would you check that type? Like if you've got a rule.
Well, so this is actually in the OpenFlow spec. The OpenFlow spec says you have to do this. You might have equipment that obeys anyway, despite that it goes beyond the spec.
It's a convenience of pyretic is to force the programmer to make ether type matching explicit.
Yeah.
And so this is making it explicit on behalf of the programmer.
Yeah.
It seems like
And I'm,
it's just a bit string, right? Like,
well, so this is something that you need to take off with the people who wrote the OS spec.
why is it worry about like which protocol?
Because it's not ether type IP, it's some other ether type ether. Those bits are not, those positions don't correspond with it.
Oh, okay.
So I release the person.
If
If the ether type something else, those bits.
It just seems like-
meaning IP.
Okay.
yeah, you could. I mean, it's not necessarily bits like 5 through 17 that contain the address.
It seems like the actual-
But I mean, you could build that logic into your, ASIC or your
It
parser.
seems like the data plane should take care of that, right? If you put a rule that matches on IP, like obviously I'm looking for IP
I
packets.
don't see open flow.
Yeah, it's just, and that's ultimately, that's the most important thing. It doesn't work this way.
It's a
So,
very common bug, and people make this bug.
Yeah.
It's actually quite irritating.
yeah,
You think it should exactly, it should promote, if you say IP address, you should think, well, duh. If the
Yeah.
Ethernet thing is not carrying an IP packet, then this doesn't make any sense. So
Yeah,
it's
yeah.
automatically set, but it's not.
Yeah.
but yeah, so, and that's what's nice about pyretic. We don't make you worry about that, but if you're implementing pyretic, you need to worry about it and getting it right. Because the one thing that is wrong with every OpenFlow implementation I've worked with is that when you install a rule that's not conforming to the OpenFlow spec, instead of giving you an error and not installing that rule in the flow table, it installs the rule in the flow table and shows you that it's there.
Right.
But it just doesn't work. And you're looking at it and you're sending packets through and you're like, it's there.
Yeah.
No packets are hitting, why not? And like, it should just give you an error. It should refuse to install the rule. But, that's life. So, we've got both bugs and interface.
And like,
You always got match the MAC addresses, so.
Yeah.
But like with SDX, it'd be a serious problem.
Yeah.
But I think-
Well, if you're using pyretic, you don't have to worry about it.
We don't have to worry about it, we're using pyretic.
yeah, that's why
It would be.
Yeah. I mean, if you ever got some like really obscure error, it could be because maybe there's a corner case I missed in this code, but now you know where to look for it. And we can talk, I can help you debug that. So then there's like all sorts of stuff which Srinivas might cover on doing bookkeeping for counters on buckets. This is like really complicated stuff because if you're adding new entries in the classifier that weren't there before but correspond to buckets you're tracking, then you need to do such and such. And yeah, so there's all that good logic in here. There's also switchify, right? Because our classifier was just a classifier. It wasn't a classifier for any particular switch in the network. So we need to strip out all of the matches on switch that we had, but we also need to specialize the classifier to every switch. So we're gonna do that over here, and in concretize, which basically takes this and turns it into a format that can be sent over this socket down to the POX backend.
Is that like a serialization?
Yeah, this is like a step in the serialization process. The serialization is not as clean as it ought to be. Omid would be awesome at rewriting this if he had time, I bet, because he's quite handy. He's gotten quite handy with Python's what the heck do they call it? Pickling facility, pickling and unpickling. There's also importizing. Oh yeah, importizing. So OpenFlow, right? When you say forward out 1 and pyretic, you mean forward out 1, irrespective of what happens. You mean what you said. Whereas in OpenFlow, when you say forward out 1, you mean forward out 1, except if the packet came in port 1. In which case, don't. So, like, oh, that's a little confusing. So this basically goes through all the rules and checks to see You know, is this rule restricted to ports that aren't itself if it's a forward? And if not, it actually turns it into two actions, one which forwards out the port and one which forwards out the OpenFlow import field, depending on what the match was. So it doesn't match on import, and then it's followed by a star rule or a more general rule that doesn't match on the import but matches on the rest of the predicate.
Seems like a lot of this one is just
Bug is spec, you know, bad design. Yeah, yeah. The vagaries of OpenFlow design. You know, and this is what we offer. We offer abstractions we think are more intuitive and more powerful and better, but this is the work that one needs to do. So there's a whole, so once you do the cross-product compilation and optimization, that's just one phase of it. And that's perhaps a very intellectually interesting phase, but then there's a whole pipeline of various transformations that need to occur, all of which have their own time complexities. And you want to make these all efficient, and I've tried to. Then there's some prioritization stuff, and then finally we get to like doing nuclear installs, where we blow away all the old rules and just write a new, slap a new classifier on it, or doing, you know, various other types of optimizations instead of nuclear install. And actually, depending on the type of switch you're using, and how it works and how its software's works, it actually may be better to do one or the other. So you're not necessarily guaranteed that like doing an iterative kind of replacement of rules in the table is going to give you better performance than doing a, you know, slam and jam, wipe it all away, blow it all away, and put it all in.
Is that configurable?
No, it's based on the software client. So if you're doing a hardware switch especially, it's based on the software client. And something like OVS, it actually depends on how many changes you're making to the table, how many deletions there are. Because if you're deleting more than, say, 50% of the rules, like, you're going to take a huge amount of overhead for doing those rule by rule deletions. Whereas it'll just be faster to blow them all away and reinstall. So this is something Srinivas found out. Yeah. So it's like, you might be worth calculating a diff, but then you have to see how large the diff is. And if the diff is above a certain size, which is going to be dependent on how the switch behaves, then you do nuclear install or not.
So,
and it just gets a lot more complex. The folks at USC, Minland's crew, they've been working on this, and they've done some really interesting studies on a variety of different hardware switches. And that's, that's all I know about that. But it's stuff that's been done. Question? No? Okay, good.
So does Pyretic choose one or the other?
Right now, Pyretic's default is nuclear, because nuclear is very easy to get right and performs not too bad in all situations. I'd love to do some more optimizations. What?
So incremental could be better, but...
It could be. We had incremental implemented, and it resulted in some really bad performance with things like, with certain dynamic things, in certain dynamic programs, we ended up getting 2x slower performance in terms of like the time it took to complete a ping all in a moderately sized network. That's not to say that doing iterative stuff isn't sometimes way better. It just depends on how much you're deleting and how much you're replacing. And we haven't had a chance to really dig into that. And it's also going to depend on how the switch operates. So a software switch is going to behave very different than a hardware switch, and different hardware switches are going to behave very differently based on their firmware clients. So there's all that kind of good stuff. And basically, this is the pipeline. And so if we come down over here, we'll see, okay, what happens?
I mean, the best series was this series, okay? There are a few games before as well. That was kind of
hold on a sec. I'm going to just raise the volume so I can hear and bring you up. Dupe. Hey, who's there? Hey.
Ever replace Sylvanas and Ragnaros if you don't have the dust, okay? If you don't have the dust, then okay, just put in Archer Commander for now, alright? If you need to get the...
Are you talking to us? I'm so confused in so many ways right now. I feel like I fell down a weird tunnel of stuff. Okay, we're going to go back to the screen share at this point. Rather, we're going back to the screen share over here. Okay, so yeah, we do get that infinite effect. To the future and beyond. Okay, so yeah, enough of this. Wow. Actually, you could probably measure the screen refresh rate of of Google Hangouts by, doing a measurement on this of some sort. Okay, so anyway, we're back. So now that I've just explained all those different stages to you, at least at a high level, so how do they work? Well, we take our classifier and we remove identities. Then we controllerify it. Then we layer 3 specialize it. Then we VLAN specialize it. Then we bookkeep it. Then we remove the buckets. Then, at this point, we launch a new process to do the rest of the stuff, because now we're gonna start doing some stuff that is computationally separable. Yeah. So we're basically gonna start this process as a daemon. And what's the process? Well, it's this F thing. And what does F on a classifier do? It is basically going to, in proactive mode, do a nuclear install. So it's kind of like we do compilation in the main thread. The reason why we do that is because we're holding the policy lock, and we need to make sure the policy stays the same while we compile it. So compilation must be finished before we can release that lock and let the policy change. But once we've got the fully processed classifier, we can let the policy go on its way, and at the same time, start our nuclear install, where we potentially do some more specialization of the classifier. And some of these stages of processing, like remove identity and so forth, these could probably be moved into the process. I kind of made the line arbitrary there. I wasn't doing fine-grained performance testing. Those seem to be pretty lightweight, and some of the others in here were a little heavier weight. But yeah, basically we're going to do some more pipeline processing, and then finally we're going to send barriers to our switches. We're going to clear their rules. We're going to send another barrier to make sure to clear all rules, and that the rules we now install don't accidentally move across. Although the barrier doesn't actually guarantee that on those switches because they're all broken, but whatever, we do our best. And then we install rules. Then we send some, requests for flow stats if we're, doing error detection. And that, my friends, is the full compilation and rule installation in Pyretic. Did the food come yet?
Yeah.
Excellent.
So,
sure.
You mentioned about this thing like controlify.
What?
Controlify.
Controlify, yeah.
Then a packet comes in, for example, if it's going to the bucket, and then you also are modifying the packet and forwarding it to some other port.
Yeah.
You send the whole packet to the controller.
If it's going to a forward bucket.
Yeah.
If it's going to a count bucket, no.
Yeah, and then it's a forward bucket. But
Yeah.
whenever you send a packet back, you this packet out. Do you send it back to the main start of the pipeline in the data frame, or just you just send it?
Oh, no. So that's the thing. Packets what OpenFlow lets you do is it lets you send packets to go out of the switch, and you get to specify the out port. But it doesn't, OpenFlow 1.0 does not allow you to send packets back into the switch for additional data frame processing. Yeah. Later variants of OpenFlow may do this stuff. My recollection is fuzzy. So at this point, we're going to stay online, but take a quick 3 minutes for people who want to go grab food right now, because I don't want anyone hungry. And we're going to get Srinivas set up to do his presentation. So Srinivas, can you hear me, my friend?
Yep, I'm here.
Ah, you are. You are. You look very handsome today, but your face is a little stiff. Do you have a video camera, or do you want to?
Yeah, I do. I'm just all I just woke up and I'm groggy right now, so I thought maybe I wouldn't show.
Oh my goodness! Person, between you and Nick's arms, it's just like overwhelming. Cool. So yeah, get your stuff set up, do your screen share, and yeah, we'll be back. I'll be back to give you the thumbs up to start in just a moment or two. I might go grab my own sandwich.
Sure.
Is the type of switch that Pyretic is controlling, is that okay for Pyretic? Or okay. So it's okay.
modular. Pyretic expects the switch more or less conform. So it expects that the switch more or less conforms to the open flow 1.0 spec. It deals with certain errors in implementing the 1.0 spec, which you've encountered in getting with OBS, which are not the full range of errors one can encounter, I'm guessing. But those are the ones we're targeting. We might have a couple of things for the PK firmware as well in there. But we expect the open flow 1.0 spec. And we may be implicitly relying, since we haven't done wide testing on, and we haven't tested on anything which we know does the open flow 1.0 spec correctly. It's possible that we may be relying on some behavior of OBS, which is extra spec.
It's amazing how all these switches are so bad.
Yeah. And are even the specs now.
Like our
They don't even implement. Basically, nothing actually. It seems like a bit lame. Basically, there's no deal with hardware. I mean, even though it's around this, you think it would be right for working.
But then you think, well, people are going to do bare metal switches and they're all going to do running that code. Some sort of code themselves, and either everybody that builds switches really sucks, or it has to be hard for some. But I just don't understand why it's so hard.
Maybe it's the hardware guys, I don't know.
Can I write code? Maybe.
Right code.
When I was first doing some consulting for Cisco and then they're asking me, what sort of people should they be bringing into the contract? And I said, you should find all your distributed systems guys. Because that's what you really control. Then, no, that's a good idea, so they all just quit and join the CRM. I'm like, oh, well, that sucks for you.
Which group is that?
This is before, this was a couple of years ago, I was working with Big Arm, very much with you.
The group that I was like talking with, it's called like SCN group. I don't know. There's it's all like CLI. We're on data slash. There was like, they had highlighted policy. It was just kind of. Yeah, okay.
But the thing I worry about the very stuff is the two sets, like the rough one, talking about it, in theory, open source, like, it's easier to get like a firewall. Then we're going to do very much, so you're going to be writing raw code, hundreds and hundreds of switches, and that's like 2 years of things. You know, it seems, it doesn't sound the right answer either.
It's just like, we know.
But still, you still need to have some sort of API. Right, if you want to have, that software is going to be working in multi-vendor environment, what is it you do?
They're not.
Right.
The API.
I don't know, I'm saying, it's just somewhere someone has to grapple with the loyalty. Talking to the hardware.
I'm really sad to be in it. You know what I mean?
So much, no.
That.
Is this Keynote or is this something?
You know, this is like, I think this is, what's in big switch.
No.
Big switch. This is they're like,
All right. Sir Srinivas.
they're like 15 one of these next case.
Hey.
Hey,
They're like 15.
I am now handing the floor over to you.
Okay.
I'm muting my microphone.
So Josh, I would need a little bit of help from you to repeat
Oh.
some of the questions that people might ask in the room, like the people who are present physically in the room.
Certainly. Well, what I'll do is I'll pass the microphone around when someone, I'll unmute and pass the microphone around when someone needs to ask a question.
Sure. Sounds great. Thanks a lot, man.
No problem.
It relates to the safer action.
Hey Josh, there
The speaker goes here.
The speaker?
Yeah.
It relates to this action.
Oh, you, what?
There's speakers back here.
How can I connect them to my computer easily?
Hopefully. Yeah, it looks like this.
Well, because I was just going to turn out like this. Or actually, anyone who's joined online can turn the speakers also.
So if we turn on our speakers, then the feedback.
Feedback is on.
That's the problem. People can't hear.
I'm going to mute the.
Oh, I guess Srinivas,
People
yeah.
can't hear us.
Yeah, I don't know.
Turn the hand or headphones.
Yeah. We should also have our own speakers and microphones. We totally stand isolated from one another. I don't think we feel like trying to.
Let's try this.
Yeah? All right.
That's what's there.
Yeah, it's Microsoft and the DDoS group.
We like to. What do you So, yeah, there was a what is that? Oh, there, oh, plug it out there.
No, remember that?
Makes sense.
Oh boy. Oh boy.
Check that.
Ooh, nice.
Hey, Srinivas, can you now speak?
Hey. I'm hearing an echo of myself though. Okay, that's better. Can I get started? Hello?
Yeah, get started.
Oh, okay, great. All right. So good afternoon, guys. I guess it's still morning here since I'm in the West Coast. It's a bit of a lazy morning because I was kind of staying up yesterday night trying to just make a few slides and organize what I was going to talk about today. So anyway, if there are any rough edges, definitely let me know. And if you have any questions, please feel free to interrupt me at any point. I just want this to be as informal as possible. So I'm going to be talking about the query support in pyretic today. I hope you guys can see the presentation as I move through the slides. So I just wanted to give a little bit of background about myself first. So I'm a PhD student who's going from 4th into 5th year in computer networking. And I've done a couple of projects working on algorithms to better manage networks. So this was some work that I did with the Coral Content Distribution Network, and then an internship at Google trying to measure the impact of their network reconfiguration in their wide area network. And one of the things that kind of stuck with me through both of these projects was the lack of good quality data that you needed to demonstrate or write good control applications. So basically, you can put in all the intelligence you want into the network, but then if you don't really have good data to act on it, then essentially all that intelligence basically is just a waste. So what I realized is maybe sometimes observing what's happening in the network is harder than what you want to do about it, or harder than deciding what you want to do about it. So around the time I got back from Google, which was this was December 2012, so that was like starting from spring 2013, I kind of sought the vague high-level goal of trying to enable some of these good measurements that would let you get this good quality data for network management tasks. So that's when the group, like Jen and others, were working on the pyretic project in full swing. So I kind of stumbled upon this question myself. So basically, pyretic focuses a lot on forwarding, and I wanted to do measurements. So why would I mix the two? And if you take a step back and think about it, it turns out that monitoring and forwarding are actually more closely related than you would think. So in fact, it does make a lot of sense. So in particular, SDN itself does provide some unique monitoring benefits. So it's possible to actually modify the data plane rules in ways that would actually make the monitoring easier. So an example of this would be the case where you're doing some kind of rule-based monitoring on the data plane. And if you wanted really fine-grained data, you don't actually have to install all the counters in one shot. Instead, you can actually do reactive specialization that would let you install only those rules that you need based on the packets that you see on the data plane. A second example of modifying packet processing to make monitoring easier would be something where you add state onto the packets to verify data plane assertion. So I'll talk a little bit more about this when I talk about the path queries work that I've been doing for a bit of time now. So in addition to modifying the data plane rules itself, like OpenFlow as a data plane gives you packet predicate level counters. So this allows you to do really fine-grained measurements almost for free, in the sense the specification mandates that you need some of these counters, and given that you have these counters, you can pretty much just use them to do the kind of fine-grained measurements that you cannot do, say, with NetFlow or SFlow. So let me just bring up the timeline of work that has gone into the querying support in pyretic. So the original prototype that Josh and Chris had built sometime around the time of NSDI 2012 had interpreted mode forwarding and count buckets. And so Josh had introduced forwarding and count buckets yesterday, and we've been talking about it. And when I came in the summer and fall of 2013, like together with Josh and others, so I had tried to put in support for proactive compilation of these count buckets. So the difference between the first and the second is that in the first case, even the count buckets would actually send all the packets to the controller in order to count the packets and the bytes for a given bucket. But in the second case, the counting would in fact happen on the data plane itself, and essentially the controller just issues a bunch of stats queries and responses to figure out the packet and byte counts of the traffic that the applications are interested in. So note that this works with a static policy and a static topology. So what that means is, suppose your controller has installed a bunch of rules, and you know that these rules aren't going to change over time, then essentially just querying the counters would give you the results that you want in terms of the total number of packets that have packets or bytes that have crossed that have been processed using that particular rule since the time you installed them. Sometime in that winter, so following fall, so basically Josh and I and others here, so we started working on providing dynamic support for queries. So what that means is, even if the topology and the policy actually change in the network, the change essentially wipes out some of these counters on the data plane. So I think Josh made a reference to this yesterday in one of the sessions. So one of the things that we wanted to do was, one of the questions we wanted to ask was, okay, how do we actually support keeping accurate counts of packets and bytes, even if the policy or the topology keeps changing and the data plane rules are in a constant state of flux? So this was something that I've been working on and been trying to get right for a bit of time, and I hope that it's kind of stable right now. So, and then in spring of 2014, I've been working on providing support for path queries. So what that means is, so far all the query support that you've seen basically tries to capture located packets which satisfy certain predicates. But what if you wanted to capture packets which satisfied certain packet trajectories? So this kind of use case comes up time and again in a lot of measurement tasks, and we thought that this was something that would be a useful primitive to implement that would essentially address a whole bunch of these traffic engineering and monitoring type use cases. So yeah, I'll just dive into a quick demo of the proactively compiled count buckets and how dynamism actually affects things. So let me just change the screen share to another window. So any questions so far while I do that?
No questions here.
Okay, all right. So I'll just go right ahead. So are you guys able to see the Emacs window? I'll just presume that you guys are. So, okay, I do see the Emacs window on Josh's Hangout as well. All right.
Large.
So, so this is,
Bigger.
what's that?
Make it bigger. Much bigger.
Oh, much bigger? Okay.
Much bigger.
Let me see. So it's possible that text edit is actually a better.
Small.
See an editor. Or maybe I'll just use the browser. I think that's better.
Yeah, you use the browser.
Right.
It'll show up better.
Okay, now we are going to have a cool infinite effect, I guess. All right. So, okay, so I'm going to open up this examples file in pyretic examples. So this is called bucket.py. So essentially what this does, so the way I've set this up is that you have a forwarding policy and a monitoring policy working in parallel composition. So this helps you test various monitoring capabilities while the forwarding in the network is still doing something reasonable. And so I'm going to actually open up a terminal and show you guys how this stuff actually works. So I'll be running test 1. Guys, I'm hearing a lot of echoes. I think somebody has their microphone on. Okay, thank you so much. Okay, so I'm actually testing this test 1, which I'm highlighting in my window. Hopefully you guys can see it. So what this does is it's actually just instantiating a query test class, which is just a derivative of the basic count bucket class, but it has some additional functionality to kind of set up the callback and print out some statistics every time it actually queries. So all that this bucket is doing is essentially collecting all packets that have a source IP of IP1, right? And I'm just sequentially composing that with the test bucket. So let's quickly see how that actually works. So I'm opening a network, which I'm starting up a network which has a single switch and 3 hosts. And I'm starting up the bucket controller. So what you actually see is once the switch connects, so let me just actually switch windows to the terminal, because I guess you guys would need to see that. Okay, right. So so once I start the controller.
Make it a little bit bigger if you can.
Okay, is that better? Even bigger, smaller?
This seems like a good size. People agree? Yeah.
Okay, awesome. So what you see is once the controller actually starts up, there is this consistent, like almost every 2.5 seconds or so, you just have this query that's actually pulling the statistics from the data plane and printing out the packet and byte counts that it sees. So far I haven't really sent any traffic on the data path, so you don't actually see any packet and byte count. So you basically just see a 0, 0. So let's see what happens if I send a ping from H1 to H2. So okay, ping went through, no problem. So you actually see 2 packets right now. So this is basically just the 2 ICMP packets. And so essentially, after a point, you start seeing these. So okay, let me actually make a correction. So the 2 packets that you saw are not both ICMP packets. In fact, since we queried in test 1 for all packets which have a source IP of IP1, in fact, the first ARP request that H1 makes to H2, and then the first ICMP request that H1 makes to H2, and then finally an ARP response that H1 sends back to H2. So it might be a little puzzling how I'm able to see all these things, but if you actually open up Wireshark and look at the packet capture, you'll be able to see exactly those packets that are being sent between these 2 hosts. And in order to be able to verify these things, if you go back to the browser, you would actually be able to see that I've included a display filter for Wireshark that would actually tell you exactly what filter you need to put into the Wireshark window, so that you might be able to see just those packets which this query is going to capture. So everyone, I hope everyone is with me so far. If you have any questions, please feel free to interrupt. So this is all well and good, but what happens if something actually changes in this topology? So far you see that if I actually do a stats request, and I actually am able to see some packets which have some rules which have non-zero packet counts, right? Are people able to see this? So you actually see that there is a rule which matches IP packets whose network destination is 10001, and its action is to output on port 1, and that actually that rule actually has been processed for 1 packet, and the ARP rule for the same corresponding network destination has 2 packets, and so on and so forth. So in fact, these are the 2 rules that actually give us the counts that we've been looking for. So in fact, you have for IP traffic network source 10001, you actually see that there is 1 packet on that rule and 2 packets on the other rule, which actually processes the corresponding ARP packets, right? So, yep. Any questions?
Yeah. So I think I think we maybe get like the tutorial might be more helpful after we kind of covered a bit more of the high level, sort of design of the system. I think this is kind of getting into the weeds a little too quick for people to follow. Feedback I've been getting.
Okay.
Is that cool?
So right now I just wanted to show how this actually works, and then I'll be talking a little bit about at a high level how this actually works under the hood. So right now I'm just showing the effects of how traffic is actually counted from the application's point of view. So that's why I was going about explaining these things. So okay, maybe I'll make this a little bit short. So the only thing I would want to say from this point is actually what happens when something actually changes in the network, and then I'll go right into like a little bit more slides. Okay. All right. So in this case, you actually do see that the data plane has the necessary information for you to be able to check what the counts for a particular set of traffic is. But what happens if something actually changes in the network? So if I bring down the 3, so the controller actually reprograms the network, and in fact, you would be able to see that there is in fact no rule which actually has a non-zero packet count. So essentially, once a topology changes, Pyretic has a built-in system where it would recognize this from some of the OpenFlow messages that are being sent to the controller, and it would reprogram the switch according to the new topology. So in a way, what has happened now is we've actually lost all the counts that were actually on the data plane. So this is where the support for handling dynamic topologies and policies actually comes in. So note that this had nothing to do, so the topology change or a policy change may have nothing to do with actually the query that was defined by the application. So it becomes necessary to support a persistent count for these kinds of buckets, even though other things might be changing around it. But you might notice that actually the counts are in fact preserved. So you do see the same packet and byte counts as before. And if you look under the hood, you would see that the way the counts are maintained is actually, there are two aspects to it. So one is a persistent count that would stay even as the topology and the policy changes. And the other is a table count, which is just something that's queried from the switch tables at any given point in time. So I'll just show that before we move on. So right now I just restarted the controller, so everything is at 0. So if I do, so you actually see that the counts have gone up to 3 again, 2. So there's no ARP, I guess. So 3. And so what you see here is actually there are two components to the count. So you actually see a table packet count and a persistent packet count. And the persistent packet count is what helps you keep the counts for the respective buckets even as the topology actually changes. So if I bring down this link right now, you see that the controller actually reprograms the switch, and then in fact the table packet count goes to 0 and the persistent packet count is now 3. So essentially, so let me just tell you at a high level how this works. So let's go back to the presentation. So if I was going too fast, please let me know if you guys have any questions. So I just wanted to show you guys what the high level, like how it actually looks when things change. And I just wanted to like give a quick demo before I moved on and told you how it kind of worked under the hood. Okay. So I hope you guys are able to see the presentation. Cool. Okay, so before we understand like many of the higher levels that have been built on top, so we first need to understand exactly how count buckets are proactively compiled in the first place. So remember that I mentioned that in the earliest version, we actually only had interpreted mode, forwarding and count buckets. And first thing that you need to that we need to think about is how do we actually support count buckets with proactive compilation. So in principle, the method is fairly simple. So we just remember the rules, those rules in the classifier which correspond to each bucket. So by tracking only those rules that correspond to each count bucket, you are then able to correlate the counts from those particular rules to those buckets when the stats responses come back from switches. So the basic mechanism is, okay, I'm going to provide a pull stats method for each bucket, and whenever there is a stats response that comes back, I use my bookkeeping structure that keeps track of the rules for each bucket in order to just pick those counts and put it into the bucket, right? So that's simple enough. And this association of rules to the buckets happens during policy compilation. So when I initialize a single bucket, as I did in this case, so I said that, so this is a little hard without sharing the code again, but basically I wrote this single line of code which said match this piece of traffic and sequentially compose it with this bucket. Basically,
if you want to go back to the code of the web browser, that could
okay. Sure.
Especially since we're looking at the slide that's a quick demo until now. So.
Right.
It might also be easier if you just share your entire screen. I mean, you can move whatever window you want to share with us to the front.
Wait, but it doesn't look like I can do that, right? Oh, there's something called a desktop. Oh, okay.
Yeah.
Okay. All right. I didn't see that. Okay. Sorry about that.
No, don't worry about it. You're not.
Okay. I apologize.
I'm doing this. It's my second. Can't find a way to do it.
Okay. Okay. Thanks for that tip, Josh. So if you see in test 1, so what I've done is I've actually selected a subset of traffic and I've sequentially composed that with a bucket. So the way the bucket actually associates those rules is when I just initialize a single test bucket, the classifier just figures out that all traffic that goes into this bucket, so essentially anything that matches, so it basically generates a single rule that says match anything, and now the action is just the bucket itself. So if you go back to core classifier, we can just take a quick look at that. Core language, sorry. So if you look at the generate classifier method for the count bucket, so what you see is actually a packet that matches anything and an action that is essentially just the class itself. So this object is essentially tagged as the cross product compilation builds on this particular classifier. So if you also check out the previous, so the way the cross product compilation works, so we saw that was the base case, like the classifier just referencing the, so basically the rule referencing the count bucket object itself is just the base case. And every time the cross product compilation builds on this particular classifier, it basically just keeps track of the count bucket object on each of the rules that are newly generated. So that's a little bit hard to show actually, because that involves going really deep into the classifier like cross compilation logic. So that's in, okay, having some trouble with the browser here. 1 second.
Also, Srinivas, in the earlier section, which I think you weren't able to join because it was too early on Pacific time, actually we dug into this code a bit. So you can assume the audience has some familiarity with it.
Sorry, I didn't understand that.
Oh, I said we dug into this code in a previous session. So
oh, you did? Okay, great. All right.
Reasonably familiar with that.
Okay, awesome.
So the difference between parallel and sequential crossing.
Okay, great. Okay, so yeah, at a high level, the rule association between buckets and counters happens during the policy compilation. So the base case is a single rule that references the bucket, and each of the inductive cases is defined separately during each of the cross product rule generations. So what happens when things change in the network? So this is all fine and good as long as you actually don't have any changes in the rules that are installed on the data plane. But when the topology and policy change, you can have a whole bunch of conditions. So first of all, the rules that were initially associated with the buckets can get deleted and be replaced by new rules. And there might be brand new rules which are actually installed on the data plane which need to be associated with the buckets. And finally, there can be new buckets that can get created which actually already have existing rules on the data plane. So by the way, I just wanted to make a quick note about nuclear and incremental compilation. So the last condition here actually only happens when you have incremental compilation, but the first two happen whether you do nuclear installation or incremental installation of rules. So the way we deal with these things is, so whenever a bucket associated rule actually gets deleted from the data plane, we use the flow removed message that comes back from the deletion to figure out the last count that was there on the data plane and then add that into the persistent counter for the bucket. So this means that you need to do a little bit more work. So first of all, you need to set up the flow removed message on any rule that you send out that is associated with the bucket onto the data plane. And second of all, when the flow removed messages do come back, you need to remember that this particular rule was associated with this bucket in this previous classifier version. So that needs a bit more work. And the way we do this is by associating the version number of the classifier with the, so essentially we associate not just the rule itself with the bucket, but we associate the rule and its version of the classifier from which it is from with the bucket. So again, this is a little bit technical because it involves a whole bunch of messages that are going back and forth and a whole bunch of race conditions as well, which we had to deal with. But basically, all that we're doing is collecting the last count that was there on the data plane, and then just adding it on to some persistent memory for the bucket. So the second case where a new bucket associated rule pops up, so essentially that's one of the simpler ones to handle, because every time you do a new compilation of the policy, you can just add on those new rules into the rules which you are tracking for the particular bucket. So this is actually relatively simpler to handle. And the final case, which is probably one of the trickiest, is when a new bucket actually gets created with existing rules on the data plane. And to handle this particular case, we subtract the existing counter value. So we first do a flow stats query onto the data plane to figure out what the existing counter value for that rule is. And then from that point on, we actually, so once we subtract this value, we can start adding the new values that we get directly from the data plane onto the counters for this bucket. So the reason why you need this is because the counters that you have on the data plane are actually cumulative. So a given rule, once it is installed, until the time it actually gets deleted, these counters just keep adding on the packet and the byte counts. So in particular, there's no resetting mechanism. Every time you say do a stats request, like there's no reset of those counters. So if a new bucket comes into existence, which references this particular rule on the data plane, but this rule has already been on the data plane for a while, it would have accumulated some counters from the period of time when the bucket wasn't in existence. So we need to actually do this kind of bookkeeping to ensure that you actually have accurate counts even as these new buckets come and go. So a lot of this code is in, let me just see, I think my browser is starting to fail a little bit. Okay, great. Are you guys able to hear me? Because my browser, I think, isn't actually responding right now.
So we can hear you, even though you don't have a browser. You could open up a different browser like Firefox or whatever, if you want.
Yeah, that's a good idea. Let me do that.
Or Safari.
Yeah, sorry about that. I just need a minute to just open this up.
No worries. Any questions in the meanwhile?
Wow, okay, really? Let me see. Okay. Sorry about the delay. So So essentially, a bunch of this dynamism code is embedded in
Increase
the
the font size,
Sorry, is that a
please.
question?
Increase the font size, please.
Oh, okay.
Much larger.
Mm-hmm.
Terrible eyesight.
Better now?
We're getting there. I think we may be there. Okay, we're there.
Okay, great. So a bunch of this code is actually embedded in the runtime and the language. So the reason why it's kind of cutting across the stack is because it really is something that needs to be deeply supported in the runtime. So the runtime is the one which generates eventually the final concrete set of rules that go into the data plane, and the buckets need to actually keep track of that. So this is where some of the stuff that Josh mentioned about the bookkeeping buckets actually comes into play. So the way we do this is actually through a process where I'm essentially just going to add correspondences for all the rules that are going to be added, all the rules that are going to be deleted, and all the rules that would stay on the data plane or just be modified with a flow mod.
Which method is this one?
So all I'm saying is we just need to.
Which method is this then? So this is inside, not remove buckets, but where in the code is this that we go up? Because we don't see the line numbers right now. Can you hear me?
I can hear you, but it's a little hard to understand what you're saying.
Oh. So where in the code is this? We don't see the line numbers.
Hey, Josh, it's a little hard to understand what you're saying, actually.
How about this? Is this better?
Yeah, this sounds a little better. Yep.
Okay. I was saying it's hard to see the line numbers. I muted my.
Oh, right. Okay. I'm sorry. Okay.
But you can hear what I'm saying. And can you just scroll up to let us know what function this is?
Ah, okay. So can you guys see this?
The function above, which function are all these ones in there?
Right.
So this is not bookkeep, it's bookkeep buckets.
Yep.
So this is the sub, okay, great, thanks.
Right.
I'm gonna mute myself and start the speaker again.
Yeah, sorry about that. I didn't, so presenting remotely is a bit of a challenge to me, I guess. I apologize. So we have this this bookkeep buckets routine, which actually does the hard work of keeping track of those rules which are added, deleted, which are going to continue to stay on the data plane and which will be modified. So in a sense, with nuclear installation, only the addition and the deletion actually matter. So in a sense, if we just focus on these two, that would those are the two things which really are exercised in this particular prototype. But then at the point when we do have incremental rule installation going, then these two code parts will also start being really exercised. So let's actually just try to understand this logic at a high level. So basically, what the collect buckets routine wants to do is take all the rules that are like essentially just get a diff between the previous classifier and the current classifier, and once it knows which rules are going to be added, deleted, modified, and not touched, it just does a whole bunch of bookkeeping actions for, in particular for each type of rule and the buckets which are corresponding to those types of rules. So essentially, we just collect all the buckets that are going to be affected by any change in the classifier. So that's what the collect buckets routine actually does. And once it collects all the buckets, the runtime just sets a condition variable on each of the buckets saying that this bucket is an update, so that you don't actually go and do some more. So essentially, it should prevent some race conditions. And once it does that, this is where a lot of the logic is, where you basically go and do some of the bookkeeping that's needed for each of these operations. So let's actually go into those functions. So essentially, all that the runtime is doing here is looking at each case for the actions that are in those rules which are going to be added or deleted, etc. And in case the action actually contains a count bucket, it just calls a simple method on the bucket itself. So in this case, you just say that you have the bucket dot add, the add match method is called on the bucket. In this case, there is a delete match method that's called on the bucket. And let's maybe ignore this for now since it's not that relevant. So let's actually go into a bit more detail on what the add match and the delete match methods do. So I guess I'll just say what they do at a high level, and then we can move on to the next thing, which is the path queries. So in core language.py, we have, let's search for class count. So, okay. So we are on line 819 in core language.py. So the add match is just doing something simple. So it creates a match entry corresponding to the match of the rule that's being added and the priority of the rule that's being added and a version of the classifier that's a new classifier right now. So as I said before, this version information is actually important because if you have the same rule that occurs across multiple classifier versions for whatever reason, then you would actually need this version information to keep track of which rule, to keep track of which version the particular flow removed message or the stats response is actually coming from. And the way we store this version information on the data plane is actually in the cookie field of the rules. So if we go back to the data plane here, where we actually showed all the rules installed on the data plane. So you actually see a cookie field on these rules. So this cookie field just tells you the version number of the classifier, which is just incremented by 1 every time a new classifier is generated. Everyone with me so far? So, okay. So I guess in the case where you actually have a delete match, so what you want to do is again add a simple entry which says that this particular match is going to be, so first of all just figure out if the match entry is in the set of matches that this bucket actually has, and if it is, then you essentially just set a flag on the particular status of the match that you actually remember that this particular rule is about to be deleted. So how does this help us? So when the flow removed message for this particular rule comes back to the controller, then the controller would send back that flow removed message to this bucket. And essentially the bucket can then do a check of whether this rule was originally associated with this bucket, and then add those counters into the persistent count that it actually has. So this logic that actually deals with the flow removed messages is in this handle flow removed routine, which you see here. And it looks a little bit complicated because of all the debug messages and stuff, but essentially the core of it is right here. So in lines 869 and 870. So what this routine needs to do is when it actually gets a flow removed message, it just looks at the particular match that's in the flow removed messages, and if it is in the matches that it has stored internally, then essentially as long as it has a to be deleted flag set on it, it's just going to increment. It's just going to add on the packet and the byte counts into the persistent packet and byte counts that it has stored for the bucket. So in essence, the logic that you need to put here is actually simple. It's just that there's a whole bunch of bookkeeping that's actually done in order to make sure that this all works together under various kinds of under different classifier versions and different sorts of ordering of events and so on, right? So I will go back to the presentation. So I just wanted to give you a quick flavor of how dynamism is handled with flow removed messages. So in effect, at a high level, what all of these changes help you do is, even if the topology keeps changing, and even if the policy keeps changing because you say have a dynamic policy like a Mac learner and you keep changing the set of rules that you've installed on the data plane, you still are able to maintain accurate counts over the lifetime of the bucket that the application has defined. And this is really helpful when you have policies that keep changing over time, and topologies which keep changing over time, which is essentially just like all the time. So maybe I'll talk about the path queries stuff. So I hope people are able to see the presentation slides now. So far, the querying support that I've talked about, they count or capture packets which satisfy located packet predicates. So this is essentially a match on a packet at a single point in time. But how about counting and capturing packets that satisfy packet trajectories? So this kind of use case comes up a lot in traffic engineering, debugging, and security. So for example, a traffic matrix is a specific case of a path query where you're saying that I want every packet that goes, so every entry of your traffic matrix in your network would be the volume of traffic that flows from a given ingress switch in your network to a given egress switch of your network. So this is essentially a query on packets that satisfy a certain condition on their trajectory, right? So the same thing applies to use cases in debugging. So if I were to figure out where along a given path a particular packet actually gets dropped, then I would essentially ask the question, okay, here's the path I'm interested in. Now tell me how far along the path the packet was actually able to go, right? And these kinds of questions come up time and again in various use cases in monitoring and traffic management. So I'll just also quickly do another demo because I think it's just easier to show what it is than to actually talk a lot about it. And so I'll just be using this cycle topology for the demo where you have, so I'm going to show this basic waypoint violation example where S4 is actually the firewall switch and you want to capture packets that do not go through this firewall switch. So actually, let's look at the code first. So any questions so far? Okay, I'll assume that there aren't any questions then. So, okay, so are you guys able to see the, so I'm in this file in pyretic examples called pathquery.py. And what I have here is, so if you go down to line 273, so the way you define a path query is by writing this function called path main. So this is like a parallel to def main, which just returns the policy on the single packet that you want to run on the network. So path main is essentially a query on packet trajectories that you want to run on the network. So that's why it's qualitatively different, and it's written in a separate routine which the runtime actually recognizes. So in this case, I'm just returning this query which is called path test waypoint violation. So what I've set up here is a bunch of what we call query atoms, which come together to form a query. So a query atom is essentially the simplest match you can do on a packet, which is just a match on it at a single point in time. So what?
Just a quick thing, Srinivas.
Mm-hmm.
When you say query atoms, you mean half query atoms as opposed to pyretic queries. Just to
right. So right.
Or correct me if I'm mistaken.
That's right. That's right. So these are path query atoms. That's right. Yeah. So this is essentially, so these are essentially the building blocks that you use to build up more complicated queries by putting them together through various combinators. So at a high level, what we have is a language which lets you write queries on packet trajectories in the form of regular expressions. And this is basically the way we actually write it. We write the basic alphabet of the regular expressions, and then we put them together through various combinators. So just like how we have basic policies like match and drop and identity in pyretic, which are then put together with the operators like parallel and sequential composition, you have a similar sort of hierarchy here. So you have the basic atoms which match packets at a single point in time, and then you put them together through these regular expression combinators like concatenation, alternation, and cleany star, right? So that's so at a high level, that's what it is. So in lines 264 to 266, I'm just defining a few basic path query atoms. So the first one says I want packets that match at switch equals 1. The second one says I want packets which don't match switch equals 4. And the third one says match switch equals 3. So when I write them together in this way, so when I say P equals A caret plus B caret C, so all I'm doing is I'm actually writing a query using the combinators caret and the plus. So the caret in this case is actually just a concatenation. So it says that if I write A caret B, then essentially it means any packet that satisfies the first path query atom, and the immediate next hop is actually the path query atom B. So essentially packets that satisfy query atom A followed by atom B, right? But I also have a weird plus in here, which is actually just a syntactic sugar for a Kleene star. So what this is saying is I want all packets that first satisfy switch equals 1, followed by packets which are not at switch equals 4 for 0 or more hops. And finally, in this case, they satisfy switch equals 3. So essentially what this subset or part of the query is doing is it's asking for all those packets which start at switch equals 1, traverse hops, none of which is switch equals 4, and then reach switch equals 3. And the other half, this pipe is actually just alternation. So what the other half of the query is looking at traffic in the reverse direction. So it's saying, give me all the traffic that starts at switch equals 3, traverses a lot of network hops, none of which is switch equals 4, and then gets to switch equals 1. So basically, depending on the forwarding policy, if packets from H1 to H3 go through switch equals 4, then you're not going to see any responses from this query. But if they don't, then you'll actually start seeing packets in the callback that we've defined here. So the register callback method, just like the other queries, lets you define a function that would take in the packet and then print out certain statistics based on print out certain basic packet headers once the query is actually satisfied. So in this case, I've set up 2 forwarding policies just for this example. So I've actually set, so since this is a cycle, the forwarding, and I'm using a static forwarding policy. So in this cycle, I'm actually using 2 forwarding policies just to demonstrate the difference. So with spanning tree 1, you actually see that at switch equals 1, you send the packet out through port 1, and in spanning tree 2, you're sending it out through port 2. So in this case, if you look at the network, it's actually the case that in spanning tree 1, the port 1 corresponds to the link between S1 and S4. So you actually expect to see that, it actually corresponds to S1 to S2. So you actually expect to see that all of the packets between S1 and S3 show up in the query. And in the second case, where you actually have spanning tree 2 with switch equals 1 forwarding packets via port 2, so you actually expect that none of the packets show up between S1 and S3 because you actually do go through the firewall switch. So S4 in this case is like a designated firewall switch. So that's why we want to catch these packets. So I'll just run these things real fast and so I'm going to first try the controller with spanning tree 1 forwarding policy. So I'll start a new network, which is a chain, which is a cycle 4, and start path query control. Okay, so in this case, the packets actually show up at the callback. So this is the print that the callback does. If you go back to the code a little bit high, you would actually see what exactly it prints. So this is the query callback, and it's just like printing the current time and saying that this is the test that we're getting the callback from, and it just prints the parameters of the packet. So it's as simple as that. So it's just printing out all the packets from 1 to 3. So let's just go over them real quick. So this is actually a packet which is at switch 3 in port 1. There is no assigned output right now, and it's from 10.0.0.1 to 10.0.0.3 because we started the ping from H1 to H3, and it's actually an ARP packet because it has an E type 2054 with a protocol 1. So it's actually an ARP request from H1 to H3, and this one is an ARP response from H3 to H1. This one's the ping request from H1 to H3. This one's the ping response from H3 to H1, and this one's an ARP request from H3 to H1, and this one's an ARP response from H1 to H3. So you actually see that based on the forwarding policy, you actually see that the packets from H1 to H3 do not actually go through S4. So they do satisfy the query because you actually are under the scenario where those packets start from switch 1, go through 0 or more hops, which are not switch 4, and then get to switch 3, or the other way around. So let's actually try the other controller. So I don't know if you're able to see this, but I'm changing the forwarding policy in my.
I'm kind of curious. How come? So this query is packets that go on a particular path. You want to see those packets. So which packets belong to the same result? Right? Shouldn't packets be grouped according to the set of packets that went on it? The packet and its predecessors that traverse a particular transformation. So if I send a particular concrete packet across, there's one of that concrete packet and it shows up at several locations.
So that's a good point. So I guess your confusion is because it's not clear. So a packet that satisfies a trajectory can actually be captured. So technically, or in principle, you can capture it at any point on its trajectory. But the point where we actually capture it is when it completes the trajectory that you have specified. So does that answer your question?
Okay, I got it. So the packet you show is the last packet along the
Right. So there are a bunch of ways in which you can do it. So you could either say, I do some analysis of my forwarding policy, and then when I see a packet that I know that in the future it would actually satisfy the query, then I'm immediately just going to send it into the bucket. So that's one way to do it. But we have taken the approach where because of the way we actually manipulate state on the packet. So I'll talk a little bit about this just momentarily. So because of the approach we've taken, so it's actually much easier to capture packets which have completed the specified trajectory. So that's actually what we print out here. So in each of these cases, you would see that this packet has actually completed the query trajectory, and then it has actually been flagged as satisfying the query, right? So actually, let me just show, even with spanning tree 1, actually, let me just show what happens with different packets. So just to make sure that it's not just showing every packet that's egressing the network, right? So if you actually check, so this is what we saw the last time, where you actually see all these queried packets. If I do a ping between H1 and H3, but if I say did a ping and H2, the path that it's supposed to take is just this one link, right? So since the link between S1 and S4 is disabled, the path that the packets actually take to go from H1 to H2, which is connected to S2, is just this one link. So in fact, it still does not satisfy this query. So let me see if there is something that would satisfy the query. So, oh, sorry, okay. So in this case, so if I actually send a packet between H3 and H4, it doesn't satisfy the trajectory that's actually specified here. So you do see that there is a hop which actually matches switch equals 4. So the packet, in a sense, doesn't even satisfy this query. So you don't actually see any callbacks being called on this particular packet. So all of them are between H1 and H3. So anyway, so I'll just change the spanning tree policy so that you'll be able to see what happens when the forwarding policy actually now routes packets through the link between S1 and S4 instead of the one between S1 and S2. So in the second spanning tree policy that I'm going to use, the link between S1 and S2 is disabled, and all the forwarding happens on the remaining 3 links. So let's check that out. Okay. So there aren't any packets that are actually reported from this query, right? So okay. So anyway, so that brings us back to that brings us back to the slide. So basically, let me just talk a little bit about how this works together. So the way we actually implement these queries on the data plane is that we observe the trajectories of the packets as they move on the data plane. And the way we do this is by encoding some information about the packet's prior trajectory into tags on the packet. And in this particular case, we use the VLAN tags, but potentially you can use any scratch space that you have on the packet. So the state that we actually write on the packet is read and rewritten by switches according to the specific predicates that you have put into the query. So all of the path query atoms that I talked about before. So this is like a 3-step process. So you take in the queries, and because these queries are written in a language which is like a regular expression language, it's a regular language. So there is a corresponding representation for these queries in the form of a deterministic finite automaton. So you take the deterministic finite automaton, this intermediate representation, and we can actually convert that into packet tagging and capture policies. So what that means is your DFA is going to have a bunch of transitions from state to state and a bunch of accepting states and an initial state, right? So we are going to take this DFA, and the states of the DFA corresponds to the tags that you actually put onto the packet. And the transition rules of the DFA are encoded as packet tagging and retagging rules, pyretic policies. So essentially, you read the initial state of the packet, and if it matches a specific predicate at that point, you just move the state, you just pop that header and push another VLAN header, which just tells you what the new state on that packet should be, corresponding to the same transition on the DFA, right? And similarly, and eventually, when the packet does get to an accepting state, it means that it has actually satisfied the query. And at that point, you just forward it or sequentially compose it with a bucket. So you can either send it to a count bucket or you can send it to a forward bucket, depending on what you actually want. So this particular example, it's actually a forward bucket, the one that I demonstrated. So once you have these packet tagging and capture policies, the thing is, these things are kind of still in isolation, right? So there is an existing forwarding policy that's already there on the network. So you don't want to create extra copies of the packet that would have these packet tags, and then that would be processed by switches in a different way. So in fact, you do want to do this tagging and capturing on those same packets which are on the data plane at any given point in time. So the final step is actually putting together these components. So you put together the existing single packet pyretic policy and the tagging and the capture fragments that we have generated from the runtime. And essentially, you just get this one huge pyretic policy that you can then finally install on the network, and that does both the forwarding and the monitoring. So note that when writing the query, I actually did not specify which forwarding policy it has to work with. So the network could have chosen to use either of the forwarding policies. So it could have picked one spanning tree or the other, but depending on which spanning tree it actually picked, the packets which actually go between H1 and H3 would either satisfy the query or not. And the query didn't actually have to change to reflect this fact. So this is kind of keeping to the whole compositional philosophy that pyretic as a whole has been built in, where you need to write applications, like write them by themselves in a modular fashion and then put them together in a nice way. So the queries can be written independent of each other, and you can just combine them. And the queries and the forwarding can be written independent of each other, and you can just combine them. And the path query library and the runtime take care of it all. So in effect, what this is doing is it's just running a DFA in a distributed fashion on the whole network. So like at the end of it, that's essentially what this whole runtime, all these rules and all this kind of processing, that's finally what it's doing on the data plane. Okay, so some final thoughts. So I hope I've convinced you that querying is useful to do, and it's useful to do alongside the forwarding. And right now, the pyretic runtime already implements accurate packet counting even when the policy and the topology are changing. And I think that's pretty useful. And finally, the path query library supports monitoring based on packet trajectory. So this last part is still work in progress. So we are trying to support a much more general language than the one you just saw there, with grouping at multiple locations and reactive specialization and things like that. And it's very much a work in progress. So any comments or feedback on that would definitely be helpful. So if you have any questions, definitely let me know. And if you want to use any of the code or any of the features that I've just shown you, feel free to get in touch with me or Joshua or any of the other folks in the group. And I definitely welcome a lot of users and developers for the code. So the final piece that I talked about, the path query stuff, it's described in detail in our upcoming HotSDN paper. So if you guys are interested in that, I definitely encourage you to look into it. And this is my contact, my last name at cs.princeton.edu. And finally, there is a long list of people to thank for this work. So I won't be mentioning all their names, but definitely, like, I've been working quite closely with Jen, with David Walker in the programming languages group, and Joshua Reich, and a bunch of other people in the group with whom I discussed quite a bit. So thanks a lot, guys. Happy to take any questions if you have.
Cool. Well, we have time probably for a question or two if anyone has any. If not, we'll probably jump to the next shorter presentation from Oleg. He's online currently. If not, we might take a little break, or if anyone has anything they want me to cover. Oh well, let's see. Keep on the turn. Hey, Oleg, you there?
Hello.
Hello.
Awesome. Hey, Srinivas. Thanks.
Hey.
We're going to switch over to Oleg now.
Oh, okay, great. Awesome.
Oh, okay. Hello, guys. I'm going to talk about the packet library of pyretic. Just a second. I'll set up my.
If you want to give yourself a quick introduction, or I can introduce you, whatever you prefer.
Of course, yes. I need. I'm confused by Hangout right now.
Okay. What's confusing you?
How to share my screen? I should press the green button, right?
The one that says screen share? Yeah.
Oh, okay.
I think you turned it on for a second in class.
Okay.
I think I'm seeing it again.
You're seeing it again? Oh, I'm seeing it too. There it is.
Okay.
Whoa.
So.
That's infinity. Beyond. Yeah.
So, can you guys hear me?
Josh, I'm just a moment.
Oh, I just took a moment?
Yeah.
Which one? All right, here we go. Yep. We can hear you on it.
So, sorry, Josh, I can't quite hear you, but do you guys hear me just fine, or?
We hear you great.
Okay. My name is Omid Alkilfad. I was a visiting student at Princeton University under the supervision of Professor Jen Rexford and Joshua Rice. And during that time, I wrote a packet library for pyretic, which is used for marshalling and unmarshalling the packets incoming and outgoing into pyretic. So before I begin, I'd like to give the functions that we will be using for the rest of the presentation. One is a pyretic packet. Sorry, I can hear echoes of myself. So a pyretic packet is a class with a dictionary that interpreter uses for matching and modifying packets. For example, when you write a match source port equals 2, the match is actually being run on a pyretic packet. A concrete packet is a packet that we receive from the pyretic backend. It has 4 fields: output, import.
Just to give context, this is in the interpreter code, not in the compiler code, correct?
Sorry?
This is in the interpreter code, not in the compiler code. So the pyretic packet library is being used.
In the interpreter, yes.
Is that right?
Yes, it is only being used in the interpreter.
Awesome. Feel free to continue.
Okay. So, so yeah, basically every packet that comes into the pyretic, which basically means the interpreter is handling it, is first gets passed through the packet library. The fields are extracted, and then a pyretic packet is created that the interpreter will use for basically running the policy. The packet that comes into the pyretic runtime system is a concrete packet that we receive from the backend. The backend sends the packet with 3 fields: import, raw, switch. The import and switch basically specify a located packet on the network. The raw is the content of the packet that we have received. And when we want to send out the packet through some output, we use the output field and send it back to the switch. Send it back to the backend, and the backend tells the switch to send the packet through that specific output. So let's see how the packet library is designed. If you look at the specification of OpenFlow 1.3, the packet pipeline has a prerequisite for each field. So for example, for Ethernet destination field, you basically don't need to have any prerequisite, so it's always available. But if you look at the, for example, IP DSCP, the prerequisite is that the packet type should be either IPv4 or IPv6. Based on this, I designed a decorator for classes that we can use to specify this relation. So if we look at the design, we can use this decorator to specify that the source MAC of a pyretic packet is actually mapped to Ethernet source. And the prerequisite for it is nothing, which is basically a true validator. And the version of the OpenFlow packet processing pipeline is 1. So if at later iterations we wanted to use the fields as specified in OpenFlow 1.3, we can just define new fields with the correct version. So for example, here we are defining a new field, a TCP source port, and the prerequisite of the field is that the packet should be a TCP packet. So we are using a protocol validator and use the TCP protocol that is passed to a protocol validator to specify the relation.
Hey, Owen, quick question about that. Why, let me turn on my, oh yeah, so why is it proto-validator TCP underscore proto and not IP underscore proto?
Sorry?
Why is protocol validator TCP, not IP?
It's a typo.
Is that a typo?
Why is protocol validator not IP validator?
Yeah, that's my question.
Oh, so I think it was a choice for the name. So because all of the specifications, if you look at the specifications, all of them have protocol. So I thought that it would be easier to read. So here, can you see that the name of the constant is TCP proto?
So to clarify, what I'm referring to is in the decorator OS field.
Okay.
Right? The third argument is proto_validator with a TCP_proto input. And that corresponds to the prerequisite on top, IP_proto, and the validator IP_proto. Oh, I see. IP_proto equals 6. Meaning TCP proto? Is that how I should understand that?
So here, the protocol validator is the IP proto field. So I could have named it IP proto validator. And then the TCP proto here is basically 6, the constant 6.
Okay, I think that makes sense.
Okay. Okay. So basically, based on this, we use this relation to specify the OpenFlow packet pipeline. So there's a problem though. For reforging the packet, each of these fields can have several meanings. Like if you look at the source port in pyretic, it can be the TCP source port, it can be the UDP source port, or an ICMP type. So it's not so clear once the packet gets out of the pyretic interpreter, how should we reforge it back into a new packet. So based on that, we decided to incrementally build the packet from the very beginning whenever the interpreter finishes its job. So we start from, so we have a few templates that we use, if I can show it. Sorry, okay.
And while you're doing this, just to clarify, this packet processor isn't processing the OpenFlow packet. It's actually processing the raw packet or the data packet that's encapsulated in an OpenFlow packet in packet. Is that right?
Yes, it is processing the raw packet of the OpenFlow packet in part. So in the OpenFlow packet in, there's a section that specifies the payload of the packet in. The packet processor parses that payload. I can show you here.
And so likewise, if someone was creating raw packets in pyretic and then wanted to inject them into the network, it would use this packet library to create the raw packet. And then that raw packet would be sent out wrapped in an OpenFlow packet.
Yes, yes. So what it does is that it doesn't know about, so the packet library basically doesn't know anything about the OpenFlow packets. The packet library just acts on raw packets that it receives. So you can think of it as a Wireshark. You can think of it as Wireshark that dissects every incoming packet. It doesn't care about the type of the packet. So it doesn't have to be an OpenFlow packet before it processes it.
Yeah, so we're just gonna have another question from the audience. Yeah, so Mike, yeah.
So I have this question, like, unlike RMP, the packet parsing part is actually embedded in the pyretic itself. Like, I think it's a duplicate effort that is being done in the parser in the controller at the moment. because you are parsing the packet again. Like you have the set of bytes, you're parsing the packet again to extract the IP addresses and all that.
No,
But
no.
if you look at the RMD paper, they have these two things separate. Like you have a packet parser that does this thing for you, and then you do matching and everything, and send the packet to the controller.
So we are not doing it twice. It's actually so you have to first unwrap the OpenFlow packet and see the raw message, and then parse that raw message again, right? Because the first parsing doesn't give you everything. It just gives you the definition of OpenFlow packet in. So you just in the first parse you just see the fields of that OpenFlow packet in. Does that make sense? I was actually trying.
Yeah, that makes sense.
Yeah, that was really helpful, clear explanation of it.
I'm trying to find the definition of packet in fields, and then I can show it to you there. I guess it would be easier.
I think it's like 3 pages up.
Okay. So based on the packet that comes out of the interpreter of Pyretic, we build a packet incrementally based on the so we build the packet based on the layers from the previous layer. So at the beginning we don't have any layers, so we need a bunch of template packets that we build the packet based on. So if you look at Pyretic code here, these are the template packets for different protocols. So based on these, so these are used as the very beginning layer when we are building a Pyretic packet. I'll just show that there's one for every protocol. So if you want to add a new protocol that is not defined, like LLDP or something, you should define a new template here. So we can use the validators to group packets together. So when we build a packet processing pipeline, we actually have a tree that while processing the packet, we only traverse a path from the root to one of the leaves. So we can actually efficiently, we don't need to explore all the paths in the tree to process the packet. So for example, if the packet is an ARP packet, we know that it's not IP, so we don't need to care about the IP fields. So the packet processor behind the scene combines all these definitions together to build a tree and make sure that you only traverse one path when you're parsing the packet. Basically, it's if I want to show it to you here, if you look at the definitions of different fields.
You can just increase the font size like twice. That would be awesome.
Sorry?
Increase the font size, please.
Oh, font size, okay. Is it good now?
Thumbs up. Very good.
Okay. Okay. So if you look at the definitions of the fields, IPv6 source IP and destination IP can only happen together when the Ethernet validator is IPv6. So what this means is that once we know that the packet is IPv6, we are not gonna check other types of fields. So we are not gonna check IPv4, IP, ICMP, or other types of packets. Well, actually, there's an ICMP v6 as well, so we might check that.
Or having some trouble with your microphone.
You have trouble with what?
Your microphone. It was making a bunch of noise to get it really faint, but now it's better.
Okay. Okay. So I'll just hold it close. So what are the benefits of the packet libraries? First of all, we are just creating a function that doesn't have any side effects. So we can just it's a thread safe function. So we don't need to care about what happens behind the scene. We can just use it on different threads and it would just work. It's easy to use. It's a single function call, and it's fast because it only traverses the path on the tree that it should traverse. hopefully it is easy to digest code as well, because the definitions of the fields are, I feel like that very self-explanatory, which, for example, here we are mapping the source IP field to IPv4 source field. I feel like that it is easy to maintain. To give an example of why it is easy to maintain, a few days ago there was an error in the ARP packet library for marshalling and unmarshalling packets. The proper fields weren't being set. So all I did to fix that was I can find it here, was that I just added 2 new definitions that say that if there's a source MAC and the packet type is ARP, just match the source MAC to ARP source MAC, and the same with the destination ARP. Thank you. That's all.
Thanks, Amit. Anybody have any questions about the packet processing library, pyretic, for data plane packet, for data plane packets being handled by the controller? One more question for you on that. This the packet processing library. Was this one developed from scratch? Was it derived from the review packet processor? What other options did you consider when designing that?
Sorry, Josh, I can't hear you really well. Could you please type it in the Hangout? It's very hard to hear you.
In the built-in. Hey, can you hear me better now?
Oh, much better. Thank you.
Okay, great. So what I wanted to ask is, when you so this code, is it code that you developed straight up, or did you modify it from Ryu, or did you, what other things did you consider? Like, what was the process by which you generated the code?
So the first thing that we used was we used a dpacket packet library for processing packets. The performance of it was really great, but the code was really hard to understand and maintain. So it was, I think the last update to it was 2-3 years ago. So we moved to use packet library, which is, so behind the scene, the packet library, the pyretic packet library is actually a wrapper around reuse packet library, and it uses Ryu for marshalling and unmarshalling the packet. So basically, the only thing that the pyretic packet library does is it maps pyretic fields to reuse fields, and also builds the proper layers once it receives it from the interpreter. So if you have VLANs, it adds the VLAN layer, or if the VLANs are removed, it removes the VLAN layer, for example.
Nice. And if I recall correctly, you also took the Ryu packet processor code and significantly improved its performance, and then recontributed that back to Ryu?
Yes. So they weren't caching a few fields, and it greatly affected the performance. I don't remember the numbers, but I think we saw a 2 to 3 times improvement over their original code. So what they were doing was that they were keeping, if I remember correctly, they were keeping a string representation of IP and MAC addresses. So when they were marshalling and unmarshalling the packets, they were just going back and forth between the bit representation and the string representation constantly. So I just added a cache that improved the performance by I think 2 times. I don't remember it.
My recollection was even more than that, but it was very substantial. That was for sure.
Oh, okay.
So, yeah, great job. Thanks for telling us about this.
Thank you.
So I think at this point, it's 2 o'clock. It's time to take a bit of a break and stretch. And depending on interest from folks who are still hanging out in Europe, you're probably pretty sleepy. If you are interested in hearing me talk more today about something in particular, like topology, etc., send me an email. I'll take a look at those before starting up the next session. And folks here, you can likewise tell me if you're interested in having me give you more brain dump, or if you'd like to, just chat about code and so forth. Okay, so see you all later. Thanks everyone for joining.